Hi, welcome. Today we're going to go over the moment of inertia of a rectangular slab. This is a slab that has width, length, and depth. So here's our slab. We'll try to draw it in 3D as best as possible. And what we're saying is this distance will be B, this will be A, and then we'll have a thickness of C. And what we're going to do first is we're going to calculate the moment of inertia through an axis going through its center of mass, which is right through the middle there in space. And then later on we're going to use, we'll try to derive the moment of inertia from scratch through this axis, about a corner, and then we'll compare that using the parallel axis theorem, taking the moment of inertia from here and then transferring it over here through the parallel axis theorem. So we're going to call this I center of mass, just for reference for the rest of the video. So let's look at it more closely. And so let's review. Remember that center of mass, the moment of inertia, by definition, is a point mass times a distance r squared to some axis of rotation. Now this is a definition. We came up with this definition because this quantity, m times the distance squared to some axis of rotation, kept coming up over and over when we studied rotational motion. Specifically, if you remember when in any textbook, if you derive the rotational kinetic energy of rotation, it's going to be related to this quantity mr squared. It'll also have, it looks like this, omega's 1/2 this quantity times omega squared, and this is why we ended up defining the moment of inertia, because it keeps coming up. Again, this is a definition, it's for a point mass. Now, for different objects, you get different moments of inertia because the mass will not be just at a point. So that leads us to the slab. So here we have our slab. We're going to do some axes. Let's do it in 3D first. So here's our y-axis. And here's our x-axis. And here's our vertical axis. Let's call it the z-axis. Now the slab is going to be here, like this. It's got some thickness. I'm over-exaggerating it so you can see. And let's say the x-axis goes right through the middle, so does the y-axis. And so there's our slab. And what we're going to need to do is we're going to have to break this slab up into infinitesimally small little units that'll go through, and they'll be kind of these rectangular little shapes. And so we're going to use our magic magnifying glass and go to the next page and see what that looks like. So we're going to take out this small, very small rectangular piece out of the slab, and we're going to have the thickness here be dx, and the thickness here be dy. The vertical thickness is still c. In this case, this quantity is not going to affect the moment of inertia because we're going to be spinning around an axis which is really parallel to this thickness. And so here's our, let's put our x-axis over here, and our y-axis is through here. And so now we've got to figure out the distance to the axis of rotation. Remember, this is our axis of rotation right here. We're going to be spinning about this axis. kind of coming vertically up like this, and we're going to be spinning around like that. So we need this distance r to this slab. Now remember that the xy plane actually goes through here. So it's that distance that we're looking for. And that's the distance we're going to call r. So this is going to be our point mass, and since it's infinitesimally small, we're going to call that dm. So using our definition, a very small inertia about this axis is going to equal its distance squared times the mass. And again, remember, I've just reversed mass and distance squared. But this is coming from the definition. We can replace r squared by noting that, using the Pythagorean theorem, that r squared is just really x squared plus y squared. So we can replace this x squared plus y squared dm. Now, what is the actual mass of dm? Well, if we say that the total mass of slab is equal to m, we know the volume is equal to A times B times C. So the density is going to equal, let's use a different variable, rho. That's just going to equal to the volume divided by the total mass, or A, B, C divided by m. So that means that the mass of our small infinitesimal mass is going to be equal to the density, rho, which is defined up here, and we assume it's constant throughout the slab, times the volume of our infinitesimal mass. If we look at the volume, it's going to be its width, dx, length, dy, times the thickness, c. So that's just dx times dy times c. Or we can rewrite that as c rho dx dy. These will just be constants. And so we're going to combine that with our infinitesimally small inertia right here. So we've got di will equal c rho, which is a constant, times x squared plus y squared times dx times dy. And that's just combining this equation with this equation right here. And so now we've got this, and then we'll be able to do our integral. Oops, well, I just moved the camera. Hopefully that won't affect things too badly. So we've got our integral. So our total inertia will equal the integral of our small inertia, which will be the integral of c rho x squared plus y squared dx dy. Now notice that we've got two variables here. Now here's the case, and this is the multivariable nature of physics in the real world. So if you look at our original drawing here, here's the x-axis, the y-axis goes through here, and this is kind of our z-axis, which we're rotating about. So x is going to go from negative a over 2 to positive a over 2, so we can get a total thickness of a. Y is changing from negative b over 2 to positive b over 2. And there's nothing we can do to relate x and y. X is completely independent of y, and y is completely independent of x. So we're not going to be able to replace either x or y in our equations here as a function of another. It just has to remain a multivariable equation. And so this is actually going to become a double integral. We can still take the constants out, c and rho, and we'll integrate x first and then y. So we've got x squared plus y squared. Remember, I just want to emphasize again where this came from. The x squared plus y squared is the quantity r squared. dm times r squared is the small quantity di, the infinitesimally small inertia. And that comes right from the definition of inertia. Stop the video and make sure that you understand this concept. I'm going from the definition through the geometry of our problem, substituting in the variables, figuring out what the actual mass of our dm was through here by figuring out the density, and then figuring out the density times the volume of our small, infinitesimally small mass, and then plugging it back in to our inertia equation. And so now we have here, again, by looking at the slab, x is changing from negative a over 2 to positive a over 2. Y is changing from negative b over 2 to positive b over 2 to get a total length of b. Now, fortunately, we're not studying multivariable in calculus, so we won't have to do this by hand. We just simply plug this into our calculator. And what I've got here is I'm going to take out my Inspire CAS on my iPad and just show you. You should be able to do this on either on your Inspire or TI-89. So here's what we got. So right here is my double integral going from negative a over 2 to positive a over 2 for dx, negative b over 2 to positive b over 2 for dy. My rho is, I actually use the letter G in my calculator, and there's c for my thickness. And when I hit the integrate button, here's what I get right here. So I get c times rho, that's my c times g, times a times b over 12 times a squared plus b squared. And that's going to be the inertia through my center of mass, the center axis of my slab. We can substitute back in for rho, and remember that rho is just the volume of the slab divided by the mass. So we've got c times a times b times c over capital M. Oh, I made a mistake. Made a mistake here. Volume is mass. Density is mass divided by volume, so it's capital M over A times B times C. dm is then the density times the volume. The volumes would cancel, gives us a mass, so that's correct. So I made a mistake here. So rho is just M divided by A times B times C. So M divided by A times B times C times AB over 12 times a squared plus b squared. You'll notice that a and b cancel here, c cancels here, and we're left with m divided by 12 times a squared plus b squared. And that's the inertia through the center of mass of the slab right here. Now, this integration, going through this process, is really the A+ level solution. Obviously, in a problem, you can always look up the inertia through the center of mass of a slab, and you could find it, and you'll see that it is indeed equal to this. So you could have looked it up. What I'm showing here is the math behind the actual calculations. Next, what we want to do is figure out, well, what is the center of mass? What is the inertia through, if we rotate the slab through an axis at one of its corners? Well, again, using the parallel axis theorem, what we've got to do, the parallel axis theorem states that the inertia through some other axis is going to be equal the inertia through the center of mass plus the mass times the distance from these two axes, the center of mass to our new axis, squared. This distance right here, if you can see, is just going to be, well, we know this is a over 2 and this is b over 2. So this distance d squared will just equal a over 2 quantity squared plus b over 2 quantity squared, which is equal to a squared plus b squared over 4. So it'll be our inertia center of mass plus mass times d squared, which is a squared plus b squared over 4. We'll plug this in. We've got m over 12 a squared plus b squared plus m times a squared plus b squared over 4. We can do some common denominators and we would indeed get a squared plus b squared times m, and then we have the quantity 1 plus 3 over 12, which is 4 over 12, and then we get m divided by 3 times a squared plus b squared. And so we can see the center of mass has actually increased. And it makes sense because now we've got more mass away from our axis of rotation over here. So this is going to be the inertia of the rectangular slab through an axis going through the corner. Now, we could actually derive this from scratch and show that it should be equal. So let's try it. So let's get some paper here and redraw this. So we have our slab. We have our new axis of rotation. And I'm still going to put in my x-axis going through here and my y-axis going through here. I'm still going to have to take out that infinitesimally small mass dm. And so let's use our magic magnifying glass and just redraw over here in this corner. So here's our small slab dm. Again, its volume is going to be dx times dy times c. And again, its distance, if you can see over here, its distance is still, we're going to call r. And that's still going to be, by the Pythagorean theorem, x squared plus y squared. So r squared will still equal x squared plus y squared. But unlike the last example where x was going from negative a over 2 to positive a over 2, this time x is going from 0 to a and y is going from 0 to b. So it's really going to be the same integral as before with different bounds. So again, by definition, so the small moment of inertia will equal to r squared times dm, r squared is just x squared plus y squared. Again, dm is going to be the density times the volume of our small slab. So it's going to be density times dx dy times c. So this is c rho dx dy. And now we're going to integrate. We have c rho x squared plus y squared dx dy. It's going to be a double integral. Let's get a clean sheet of paper. And so in this case we have, for y is going to go from 0 to b. From x it's going to go from 0 to a. C rho times x squared plus y squared. We plug this into our calculator. And let's see what we got. I'm now going to use my, see if you can see it here, I'm going to use my Inspire on my iPad. All I'm going to do is change the bounds, so y will go now from 0 to b. X will go from 0 to a. And remember, my g is rho and there's c. I should hit enter, and here's my result. So my result is a times a squared plus b squared, b times c, and remember g is just rho for me, all over 3. And so let's see, I can combine a, b, and c over here, times rho over 3 a squared plus b squared. Remember, rho is just going to be the mass divided by the volume of the slab. So I've got a, b, c over 3, mass divided by a, b, c, a squared plus b squared. And you can see that a times b times c all cancel, and we're left with m over 3 a squared plus b squared, which is exactly what we got when we used the parallel axis theorem before. If I can find that piece of paper, right here from the parallel axis theorem. Same result. So we just proved that the parallel axis theorem actually works, at least for the slab. We did the calculus behind it. Again, this is the A+ solution, so you can see the math behind it. I hope that helps and shows you how moment of inertia is actually calculated from scratch. But again, it shows you that we can still use the parallel axis theorem and just look up moments of inertia in our tables. Good luck. Thank you very much for watching.